All right, Gen Chem kids, we are going to talk some more about radioisotopes today, and we are going to talk about stability, and hopefully with the PhET that you did a couple of days ago, you kind of understand what makes an atom stable versus unstable now. And we're going to also talk about radioactive half-life and some of the applications we have for radioactive half-life today. So I want to go back and kind of debrief on the PhET that you did last time. And you were supposed to look at the ratio of protons to neutrons in that PhET and determine what kind of ratio made the atoms stable. So I want to just review some of that. So why are some isotopes of an element stable and others decay or have radioactive decay? Hopefully you have this kind of an idea going. It all comes down to the ratio of the protons and the neutrons, okay? So what happens is if we have the correct ratio of protons to neutrons, that allows for that nucleus to be stable. But if we don't have that ratio, that makes it so the nucleus is unbalanced in some way with the strong nuclear force, and it makes it so that the nucleus will decay in some way, either alpha, beta, or gamma, or even positron or electron capture, which we haven't talked about, in order to get that ratio to be better. So here's a graph that goes along with that ratio. And I'm going to make it a little bit smaller so that I can keep it on the screen here. So if I make this a little bit smaller, notice on the bottom we have the number of protons, and then on the y-axis we have the number of neutrons. And hopefully when you did your PhET simulation the other day, you came across that if I had a ratio of neutrons to protons, if I had about 1.16 neutrons to 1 proton, that made it stable. So if I look at this graph, here's my 1-to-1 ratio here. You'll notice at the very beginning, when our elements are pretty small, we are pretty close to that 1-to-1 ratio. But as our elements get larger and larger, we get farther and farther away from that line. Notice we are really focusing on the black line here in this graph. These black squares are the stable isotopes of the elements. Okay? And as we get even further away, we get to almost a 1.5 neutron to 1 proton ratio. So 1.5 is about right here. Okay? So stable elements fit within a 1.1 to a 1.5 neutron ratio to 1 proton ratio. This is where our band of stability is. Okay? Now, notice after a certain point, we have no more stable isotopes. Okay? So let's take a look at some of these questions here. Here's another way of looking at it. This just gives us the stable isotopes, not all the isotopes. Notice we have our 1.5 to 1 line and our 1 to 1 line, and all the stable isotopes fit pretty much within those two ratios. Okay, so what seems to be the ratio of protons to neutrons that is stable? And how do we calculate the ratio? Now, what we normally do when we calculate the ratio, we think of neutrons divided by protons. That's how we do the ratio, or we'll do it neutrons to protons. Now, notice in this graphic here, we have 1 to 1 to 1.5 to 1. So I would say our ratio is 1.0 to 1.5 neutrons to 1 proton. That would be where our stable elements lies. Now, this next question, is there a number of protons that even the ratio of protons to neutrons is unstable anyway? Let's go back up to this other graph. Notice once we got above this line, there was no stable isotope at all. And that was 82 protons. So if we look at our periodic table, 83 plus protons is always unstable, regardless of what the ratio of protons to neutrons is. Okay? So that means 82 protons is our last stable element. So let's look at our periodic table to see what element that is. And let's get my periodic table up so that we can look and see what element that is. So if I look at periodic table and I look for 82 protons, 82 protons is right here. It is the element of lead. Okay? So lead is our last stable element. The largest or the biggest stable element. Every element beyond lead on that periodic table. So let's go back to that periodic table and let's switch colors here. So every element beyond lead, bismuth, polonium, tacetine, radon, radium, francium, all of these elements, and even these down in the lanthanide, actually not the lanthanide series aren't. Let's erase that. The lanthanide series are just fine. It is the actinide series. These are all, every single one of them, these are all radioactive. Okay? So these are all radioactive. There's no stable isotope of any of these elements out there at all. Okay? In fact, everything beyond, let's highlight this even further. Everything beyond here, beyond uranium, this is all man-made. This is all made in a laboratory. Uranium is our last naturally occurring element. Okay? So, let's look at this. Bonding energy. Why do some elements fuse and other elements break apart? Fission. So we have two types of radioactive or nuclear reactions. We have fusion, which is putting elements together, and fuse should give you the idea that we're fusing things together. So fusion is the binding of two nuclei. Binding of two nuclei to make a larger nucleus. Okay, so when we fuse or do fusion, we are taking two small nuclei and we're putting them together to make one big nucleus. And fission is the exact opposite. We're taking one big nucleus and we're breaking it apart into two smaller. So we take one nucleus and we break it apart into two smaller nuclei. Okay? So fusion, where you're fusing or putting together elements to make a bigger nucleus. Fission, we're taking a big nucleus and we're breaking it apart into two smaller nuclei. Okay, so I have some questions here. What happens to the energy when you put two hydrogens together for helium? So let's look what it does to this energy. This is our graph on energy. So if I take two hydrogens and I put them together and I fuse them together to make helium, here's helium right here. Look at how much energy is released. We get a ton of energy off of that. So this is the energy released. Okay, we get a lot of energy. Okay, now that is the reaction that's going on in the sun. That is the energy that our whole entire universe runs off of. Or I shouldn't say universe, solar system. Our solar system is what is going off of our sun. So we get a release of a lot of energy. Okay, it's a lot of energy. And, our whole planet runs off of solar energy. And just think, we don't get very much of the sun's energy this far away from the sun. Okay, let's look at this. What if I took two lithiums and put them together to make a carbon? So let's look at two lithiums right here. If I took two lithiums and put them together to make a carbon, I would get this much energy. I would still get energy, but I wouldn't get nearly as much as if I used hydrogen to make helium. So I still get good energy, but it would be less energy. It would be less energy than when I fuse hydrogen to make helium. So I get less energy. Okay, so what happens as I go along here and I keep adding elements to each other? I'm going to erase this. What if I added two carbons together? Two 12s would give me about 24, so that would give me somewhere in here. I'd still get some energy, but not a lot. And as I add two 35s together to get a 70, let's see, 70 would give me right here. That's still a little bit of energy, but not very much. As I go up and up and up, I still get some energy, but not so much. So I want to think about this. Where along this energy curve does that energy peak? What's the top energy bond that we have? If you said iron, you're right. So look at this. Iron is the top of that curve, isn't it? Okay. And as we go up this energy peak, as you go up in mass along the periodic table and fuse the elements, what happens to the amount of energy gained? It gets smaller and smaller and smaller. The energy gained gets smaller and smaller until you reach iron. Iron is the energy peak. So, question here. So as our sun in our solar system is taking hydrogens and fusing them together to make lithium, and helium, and that's what's generating the energy in our solar system. What happens when it runs out of helium and hydrogen? And then it goes to lithium, and it fuses lithium together to make carbon. What happens when all the lithium's used up? Then it will start fusing carbon, and it will start fusing other things. And all of a sudden, all of those things will be used up, and it's made iron. What happens when there's nothing else to fuse? Because remember, once we reach iron, iron's the top of that energy peak. So if there's only iron, if I fuse iron together, I actually get less energy. So that's not going to happen. So my question is, how do these heavier elements get made? We know we have elements beyond iron. How are they made? Because once the sun gets to iron, that's where we have what's called a solar death. And that sun dies because it has nothing left to fuse. So how does it work? So what happens if I have a sun that is big enough, or a star, I should say a star that is big enough, where the iron core is there in the middle? That iron core becomes so heavy and so dense that as it starts to die, it starts to collapse on itself. And then as it starts to collapse on itself, it sends a shockwave back out. If you've ever seen an explosion, you've seen a shockwave go out of an explosion. As it collapses, it sends a shockwave back out as it collapses. And that gives a lot of energy for an explosion. And if you've ever heard of a star going supernova, that's what that is. It's the shockwave of the collapse or the death of the star going back out. The star becomes what we call a supernova star. And that supernova explosion actually creates quite a lot of energy. And it creates so much energy that we're actually able to fuse even heavier elements because we're using the energy from the explosion to fuse the big elements. So when we talk about the heavy elements being made, they are made in a supernova. Explosion. And that's where we get all of the elements that we see that are beyond the periodic table, beyond iron. So if we're looking beyond iron on the periodic table, that's where all of those elements came from. They came from a supernova explosion of a big star. Okay? So I hope you realize that we have two types of reactions here. The reactions in stars are called fusion reactions, but we also have fission reactions where things are broken apart. Okay? So let's talk about half-lives now. And let's talk about fission a little bit. Fission is where we are looking at things breaking apart. So let's look at this energy curve once again. I'm going to get another color. Notice if I look along this curve, if I break uranium into two smaller elements, I will go and I will get, let's get that energy. I will get a little bit of energy here. Not a lot, but compared to fusion, but I will still get some energy if I break that uranium into two smaller atoms. So this is where fission goes. If I break that uranium, make it into two smaller atoms, I will get this amount of energy right here. So we would expect fission to be along the heavier elements, because if I break the heavier elements into lighter elements, that's the only place that I get an energy gain. Okay? So we would expect fission to be only with the very heaviest elements. Okay? So When we looked at the amount of energy that was given to us or returned to us, which gave us more energy? Fusion definitely gave us more energy. We got a lot more energy when we took 2 hydrogens to make helium than we got when we broke uranium into, let's see, what would uranium break into? It would break into it would probably break into a barium and, let's see, barium and an iodine. Okay? This would be fission. This gave us a lot more energy on a magnitude of about 10 times. Okay? So the key to energy is if we ever figure it out, if we ever figure out how to actually do fusion on this planet, our energy problems will be solved for sure. Okay, radioactive dating, half-life. So half-life is not just a game, it's actually a scientific concept, a nuclear concept. So half-life is the time it takes for half of the radioactive sample to undergo decay. And that decay could be alpha, beta, gamma, positron, or electron capture. Okay? Any type of radioactive decay, it will happen randomly, but by the time half of the material undergoes decay, that time that it takes is the half-life. So I want to show you the decay series for uranium-238. Now, uranium will decay spontaneously because it's a heavy, heavy element. So it will go through this whole decay series. We'll have uranium doing an alpha decay. Notice the red arrows are alpha and the blue arrows are beta. So our first decay is an alpha decay to thorium. And then we will go to praseodymium and uranium once again. Now notice this time, instead of uranium-238, I have uranium-234. I have a different isotope. Then I will go to thorium once again, but once again, a different isotope. Instead of thorium-234, I will have thorium-230. And then I will go to radium. Then I will go to radon, alpha, 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 then alpha to polonium, another alpha to lead-214. Okay. Then bismuth-214, polonium, once again, same isotope, but different mass, 218 versus 214. Then lead again, different isotope, but same element, bismuth, different isotope, okay, of polonium, and then down to lead-206. Finally, when I get to lead-206, I have a stable isotope, okay? Now, notice in this whole series, we had different times on these half-lives. So this first half-life for uranium to decay to thorium was 4.5 billion years. And then we have 24 days for this one and 1.2 minutes for this one, 250,000 years for this one, 80,000 years for this one, 1,600 years, 3.8 days, 3 minutes, 27 minutes. This one's 20 minutes, 160 microseconds, 5 days, 21 years, 138 days. So my question is, why are the half-lives so different? Why are, oh, that's a horrible R. I want this to let me erase. Why are the half-lives so different? Think about it. I'm going to give you a symbol for half-life. Half-life is designated by lambda, our Greek letter lambda. Do you think maybe the half-lives are different because of the distance things are from that ratio of 1.5 neutrons to 1 proton is? If you graph out these different isotopes, you'll find that the farther that isotope is from that 1.5 to 1 ratio, or actually this is neutrons on this side, protons on this side, the farther that it is away from that ratio, the faster or the shorter that half-life is. The closer we get to that ratio, the longer that half-life is. So that ratio even designates how quick or how slow the half-life is. Okay, so here we go. Half-life means that we are going down by half every time we progress a half-life. So if I start with 10 grams of strontium-90, for example, times 0, the half-life of strontium-90 is 29 years. So if I go through 29 years, I would expect to have 5 grams left. If I go through another half-life and I'm now at 58 years, I would expect to have half of 5 left, which is 2.5. It doesn't go to 0, it's half of a half, which is a quarter. So I would have 2.5. So if I go through yet another half-life, what's half of a half of a half? Let's see, a quarter divided by 2 is going to be an eighth. So I would have 1.25 left. And if I go through yet another half-life, a half of a half of a half of a half. Let's see, an eighth divided by 2 would be a 16th. So I would have 0.625 grams left. So notice I never will technically, this is an exponential equation here. Notice I never technically mathematically get to 0, but eventually physically I would get to the last atom to decay. Okay? So mathematical representation does not necessarily go with what's actually happening with the atoms. It gives us a good approximation. Now here are some different half-lives of different isotopes. We have polonium, which has a half-life of 163.7 microseconds, cobalt-60, which has 5.272 years, radon-222, which has 3.8 days. By the way, have you had your house tested for radon? Radon is a thing here in Utah because we have a lot of uranium in the hills back here for the granite mountains that we have, and uranium decays, and radon-222 is part of it, and radon is a big producer of lung cancer. So make sure that your house has been tested for radon, okay? Phosphorus-32 has a half-life of 14.28 days. I used to use phosphorus as a radio tracer for a lot of the molecular biology labs that I used to do. Carbon-14 has a half-life of 5,730 years. We use that a lot in anthropological studies to see how old different sites are and different animals and different human remains are that we see. And then uranium-238 has a half-life of 4.46 times 10 to the 9th, or 4.5 billion years. Okay, so let's look at carbon dating and why we use carbon dating for anthropological sites. Okay, anthropological sites are just prehistoric sites. Okay, carbon dating makes use of the radioactive decay of carbon-14, which is formed by cosmic rays in the upper atmosphere at a fairly constant rate. So that's formed above the ozone, above about 16 kilometers in the atmosphere because of the UV rays coming in and hitting the nitrogen in the atmosphere and zapping that nitrogen and making it carbon-14 instead of nitrogen-14. Okay? Those carbon-14 atoms become evenly spread out throughout the Earth's biosphere, where they mix with stable carbon-12 and carbon-13 atoms. Plants use carbon dioxide from the environment, which contains all three of those carbon isotopes. And we use that to build more complex molecules through the process of photosynthesis. And then organisms like us, we use those plants to fuel our bodies. For example, I got some nuts here that came off of plants, right? And the carbon that the plants use to make these nuts are now going to be in me, making me once I eat these cashews. Okay? So, because organisms are constantly taking in carbon compounds, all living organisms contain the same ratio of carbon-14 to carbon-12 and carbon-13 that's found in the atmosphere. However, when organisms die, we no longer are taking in carbon. So the carbon-14 that makes up us or other organisms starts to decay. And so we can compare the ratio of carbon-14 in that object compared to the carbon-14 ratio in the atmosphere and give a pretty good approximation of how old that object actually is. Okay? So that's how we do that. So we know that the half-life of carbon-14 is 5,730 years. So this is how we do. If I have only 25% of the carbon-14 that I would expect in an object that is current, how old is the object? So let's do this. We're going to pretend that we're going to start with 100%. So to go through one half-life, I would have 50% left. So one half-life is 5,730 years. But I don't want 50%, I want 25%. So let's go through another half-life. So another 5,730 years. Half of 50 is 25%. So let's add these two up. 5,730 years plus 5,730 years will give me 11,460 years. So I know that that artifact is somewhere about 11,000 years old, plus or minus about 200 years. That's the error window there. So I can say that that object is 11,660 years old to 11,260 years old. Somewhere in there is what we would expect that object to be. Okay? Example 8. How much of a 10-gram sample of americium-241 remains after 4 half-lives? Okay, so I'm going to start with my 10 grams. And we're going to go through 4 half-lives. So one half-life will get me down to 5 grams. So there's one. My second half-life will get me down to 2.50 grams. My third half-life will get me down to 1.25 grams. And what's half of 1.25 grams? There's my fourth half-life, right? I want 4 half-lives. So this would be 0.625 grams. So I would expect to have 0.625 grams of americium-241 left. By the way, we use americium-241 a lot. If you have a smoke detector, and please tell me you have a smoke detector, we use americium-241 in smoke detectors. It's what makes the smoke detector work. Okay? So let's do this. If the passing of 5 half-lives leaves 25 milligrams of strontium-90 left, how much was present at the beginning? So let's do the reverse. So if I have 25 milligrams, we're going to reverse this. So if I go through a half-life, that half-life before, I would have had 50 milligrams, right? And if I go through a half-life before, 50 times 2 is 100 milligrams. So that would give me 2 half-lives. I want to have 5. So let's keep going. What's twice of 100? It would be 200 milligrams, right? But I want 5, so I need to do another half-life. So twice of 200 is 400 milligrams, but I want to do even more. So here's my 5th half-life. So I would have started with 800 milligrams. Okay? So, all right. So there's how we deal with these problems, these questions. Here we go. The Shroud of Turin is thought by many to be the burial cloth of Jesus Christ. It's a length of linen cloth bearing an image of a man who appears to have suffered physical trauma in a manner consistent with the crucifixion. Radiocarbon dating was completed on this cloth in 1988 by 3 separate laboratories. The samples they tested date the cloth to be about 750 years old. So, if the cloth is 750 years old, 1988 minus 750, let's see, 8, 3, 2, that would be about the 1200s. So, is that the time that Jesus was supposedly on the face of the earth? No. So, this is the time of the Crusades. Okay? So in the Crusades, relics were all important. So we feel like this was a relic that was manufactured during the Crusades. Okay, so that will take it for today. And I will put some assignments using half-lives on here for you so that you can practice that. Have a great day. We'll see you later. Bye.